Here we have a rational inequality that we want to solve and then give our answer in interval notation. To be able to solve a rational inequality, we want to start by finding some key features of the graph, places where the graph could potentially switch from being below to above the horizontal axis. So the two key pieces of information that we need to know are where are any horizontal intercepts and where are any vertical asymptotes. So let's look at finding those first. So to find horizontal intercepts for a rational function, we think about solving our function equal to 0. So we're really thinking about when is x minus 6 over x squared minus 64 equal to 0. But if we cleared the fraction by multiplying both sides by x squared minus 64, we'd just be left with x minus 6 equals 0. And this really is our strategy. Anytime you want to find a horizontal intercept, you're just going to set the numerator of your function equal to 0 and solve for x. So adding 6, we get x equals 6. So this particular function has one horizontal intercept at the point 6, 0. Now let's find any vertical asymptotes. Vertical asymptotes come from places where our function is undefined. So we're looking at our denominator and setting that equal to 0. So notice for the horizontal intercepts, we set the numerator equal to 0. For the vertical asymptotes, we're going to set our denominator equal to 0. Solve for x. Adding 64, we have x squared equals 64. And then we can use our square root property. The square root of x squared is equal to plus or minus the square root of 64. So x is equal to either plus or minus 8. So these are equations of two vertical asymptotes for a function. From here, what we're going to do is we're going to sketch the graph of our function. We can definitely use some technology to help us out here as well. But first I'm going to draw in a horizontal axis, a number line, and mark in those key values that we found. So -8 and +8, where we're going to have our vertical asymptotes, and then also +6. So I'm going to go ahead and mark a point here at 6, 0, and then I'm going to think about where I've got my vertical asymptotes. I sketch those in as a dashed vertical line and put an open circle at that x value to remind me that this is a place where the function is undefined. From here, take a look at the graph on your calculator or plug in some points in each one of these intervals. If you take a look at this graph on your calculator, you'll see that to the left of -8, we have a section of our graph shaped like this down below the horizontal axis. In between negative and 8, we have kind of an S-shaped piece of our curve that crosses through at +6. And then on the right side of 8, we have a piece of our graph that is up above the horizontal axis. So here's what's important for us to look at. On the left side of -8, all of the points on our graph are down below the x-axis. In between -8 and +6, all the points on our graph are up above the horizontal axis. In between 6 and 8, all the points on our graph are down below, and then to the right of 8, all of the points on our graph are up above. So now look back to the original problem, the inequality that we started with. We wanted to solve when is this function less than or equal to 0. When we think about being less than 0 graphically, this means that we want all the places where our graph is below the horizontal axis, or the x-axis. So this section to the left of -8 is where it was down below, and this section in between +6 and +8 is where it is down below. So to be able to write out our solution in interval notation, remember where we have a vertical asymptote, the function does not exist, so those x values cannot be included and must have a parenthesis. Where we have a horizontal intercept, that is a point on our graph where our function is equal to 0, and so that can be included and we'll have a bracket. So that left piece of our graph is going to go from -infinity to -8 with a parenthesis, since -8 is an x value for our vertical asymptote where our function is undefined. And then we're also going to go from 6 with a bracket because 6 was a horizontal intercept. It's an actual point on the graph where our y value is equal to 0, up to +8, but with a parenthesis at 8, since 8 is where we have a vertical asymptote and the function is again undefined. So one way that we can find where our function is less than or equal to 0 is to look at the graph and look for where it is below the horizontal axis. The other way we can do this is to test points. So for example, if you picked a point to the left of -8 and plugged that into your function, we could check to see if that gave us a value that was less than or equal to 0. So for example, if we were to test the value x equals -9, so that's something to the left of -8, we would take -9 minus 6 and then -9 squared minus 64. So -9 minus 6 is a -15. In the denominator we have 81 minus 64, which is 17. So we end up with a fraction, -15/17. But the key thing is that this is a value that is less than 0. So this makes the original inequality a true statement. So that means that it is part of our solution set. So thinking about that graphically, so here would be our -9. We found that this section of our graph comes out true when we plug in a value. But if you test a value that is not in one of the regions that we had in our solution set, for example, if you were to test x equals 0, you would have 0 minus 6 all over 0 squared minus 64. Well, -6 over -64, the negatives cancel, and we end up with a positive fraction instead. We have positive 3 over 32. Well, this is greater than 0, which means this makes the original inequality false. So here's 0, and this part comes out false. That's why it's not part of our solution set. So one strategy for finding the solution is to use the graph to look at where it's above or below the horizontal axis. Another strategy would be to test values from each of the intervals that you have to see if they come out true or false in the original inequality.